This lecture will be a little sidebar on muons. The only thing new after that last lecture was we said that lengths are contracted. Moving lengths shrink by this amount. It doesn't matter. Remember, we said the prime is the one that measures the object at rest. So today, right now, this lecture, I just wanted to go over muons. Muons are an elementary particle that was actually discovered in 1936 by Carl Anderson at Caltech here at Pasadena. Now, what are muons? Well, muons are just like electrons. They taste like one, they look like one, they smell like one. Matter of fact, you could even make hydrogen by putting a proton with a muon going around it. Right? You can make atoms with muons. They're exactly the same. They're exactly like a muon. Well, then how are they different? Well, they're just a lot heavier. The mass of a muon, we'll use this symbol for the muon, mass of the muon is about 207 times more than the mass of the electron. So it's 200 times heavier, quite a bit heavier. How come we don't see them all over the place? Well, because they don't last very long. They decay. Well, what do they decay into? Well, for one thing, they have to decay into something smaller than themselves. You can't detect. Actually, let me just, it's not the mass, it's just the muon. Here's the muon. Has to decay into something smaller. Well, what's smaller? An electron is smaller, so, and this is a negative charge, just like the electron is. But it can't just decay into one object, because momentum wouldn't be conserved. It's like an explosion where there's only one piece flying out. You'd never get that, so you have to get something else. You actually also get a neutrino right here. This is a neutrino. We'll come to these later, but neutrino. But it can't just go into an electron and a neutrino because there's something, a conservation law that says conservation of lepton number, which we might talk about later. And this has a lepton number of, let's say, -1, or let's just say 1. This has a lepton number of 1, and that has a lepton number of 1, and 1 doesn't equal 2 right here. So we need another particle to, and so what we get here is we also get a neutrino, and I put a little bar, that's the anti-neutrino. That's what that little bar means, anti-neutrino. And there's different types of neutrinos. This is actually the electrons. He has his own neutrino, and this is the muon's neutrino. So this is what it decays into. And it does it fairly fast. Suppose you wanted to measure this half-life of this material right here. Well, first of all, where are you going to find muons? Well, if this is the Earth, way above the Earth, upper atmosphere, you got cosmic rays coming in, cosmic rays, protons and so on, protons, let's just say fast protons. They run into atoms, create a shower of particles right here. And one of these particles that is eventually created is the muon right here. So we've got muons coming down right here, muons coming down from, and they're just created up in the upper atmosphere. Now, this is probably the most dominant radiation we're hit from up above. Maybe from the Earth, it's radioactive stuff in the dirt, but up above, it's just these muons right here. We're getting hit by about 1 per square centimeter per minute. So every square centimeter is about 1 per minute going through. So if you add up all your square centimeters, there's probably quite a few per second maybe going through us right now. They go right in, out the other end. Right? How far do they, when they hit the Earth, they go down into the Earth maybe 1,000 feet. So if you want to get away from getting hit by these muons all the time, go down into a deep mine shaft about 1,000 feet and you can finally see, I'm not getting hit by these things anymore. So Now, how are we going to measure the half-life of these? Because these guys are going awfully fast. We have to stop them if we ever want to measure their half-life. So let's get this certain type of material. Here you can buy a type of material. It's called a scintillator. Scintillator. They come out of plastic, certain types of glass, even a liquid right here. But what happens is when a charged particle goes through this, you notice here it's going to be running into atoms as it goes through there, and it's going to pop out a little slower out the other side. And the loss in kinetic energy it had, the amount it loses, is all going to go into light. So it's going to create a tiny amount of light that came out of here every time one of these goes through. That's what a scintillator does. Now, there's a lot of other light in the room hitting this thing right here, and you don't want that to do it. So what you do is you wrap this really good in black material right here, so no light can get in. And on one end, let's wrap it over here, and we'll open up this end. This end right here, I'm going to put on something called a photomultiplier tube. Photomultiplier tube. What that does is it takes this little amount of light and amplifies it, and it gives you a little pulse coming out the other side. Gives you, it looks like that. The more light, the bigger the pulse. Matter of fact, the area of this is related to how much kinetic energy it lost, but I don't care about that. Okay. Now, if I take this device and put it into something called a discriminator, what that does is that'll turn this pulse into a digital pulse. So it'll give me a digital pulse. It has a level on there, and so if you put the level here, you won't get it, but if you put the level below the peak, you get a pulse out right here. And so every time a flash of light goes through, you get a digital pulse out. Okay. So now, what do I want to do? Well, let's say we take 3 of these detectors. Here's one of them. Let's call this detector A, wrapped in a PMT on the sides. And we'll make a sandwich out of it. We'll make the middle one a little smaller right here. Here you got a PMT, and you got another one down here. We got 3 of them sitting on top of each other. PMT. And they're all going to go into my discriminators. So we've got 3 discriminators right here. Discriminators. Okay. So I get 3 digital pulses coming through. So now, if a muon goes through, I get a pulse here, I would get a pulse here, and I would get a pulse there. Out of both A, B, and C. So this is going to be my A, my B, and my C. A, B, and C. Now what I want to do is I want ones that will stop here. If I wanted to stop here, that means I want to hit there, and not there. So what I can do is I can plug into another unit right here, something called a logic unit, where I can apply ands and ors and nots to it. And so what I want to do is I want it, when I get an A and a B and a not C, maybe not C will be a little bar over it. So I want, when I get a signal here, a signal there, and no signal there, then I want a pulse coming out. That only time I'm going to get a pulse is if I get a pulse here, pulse there, and not a pulse there. What happened then? That meant that this muon came down, stopped right there. Now this doesn't happen very often. Only the slower ones will do that. Most of them go down 1,000 feet underground. So the amount, even though we're getting hit by a few of them every second in our body, you might have to spend hours before one of these happens, even with a big area right here. So it takes a long time to do this experiment, sometimes weeks right here, just because this is very rare to have it stop there. Okay, so now what I want this signal right here to do is I want this to go to a clock, a stopwatch, a digital timer. And this is going to be my start signal, start. This is the start on the stopwatch, right there. Now, I'd like this signal, this pulse, with a little screw, I can make this as wide as I want. I'm going to make this about, say, 100 microseconds long, right here. I want this to be pretty long, right there. Okay, so now I've started the stopwatch. Now I need to stop it, right here. Well, what's going to happen? Now I'm waiting, this muon stopped, he should decay. He should decay by this process. It could be something else, but this is the dominant process right here. Now you can never see these guys. These are like ghosts, forget about it. But this electron, all of a sudden, when this thing explodes, you get a little electron flying off here. Bang. It's not going to leave this detector. It'd take quite a bit to have an electron leave it right here. Remember, it's not that heavy. But that little electron's going to run into atoms and create a flash of light right here. And I won't get a flash of light there, and I won't get a flash of light there. I'll only get one in this one. So what I'm going to do is I'm going to take my 3 signals here, these 3, and plug it in to another, sorry, not here, on the other side of the discriminator. I want to take them from right here. I want to take there, there, and there, and I'm going to put them into another logic unit. And I want only when I get a hit here and not there and not there. So I want not A, B, not C. Not A, B, not C. And that, I'm going to get a little pulse coming out. That doesn't have to be very long. That pulse comes out. And that's going to be my stop from my timer right there. So I have a start and a stop. And after I hit the stop, it records the time and resets it. Now, it might be that maybe this was just a fluke that these two got hit, and it never really stopped here. And so I could get the start, but I might never get the stop. So what I'm going to do is, by the end of this pulse, if you don't get a stop, then reset it and get it going again right here. So it means there was probably something wrong here. So right here, if you don't get a stop by then reset. If not a stop. Reset. Okay. So what am I going to get? Start, stop, start, stop, start, stop. Right here. What I'm going to get is a list of times. So I'm going to get a bunch of times right here. Times. A whole bunch of times right there. And now if I were to plot those out, these times. So on this axis, I'm going to plot the time. And this, I'm going to plot how many I got at that time. So let's say I go from 0 to 1 microsecond, 2 microseconds, 3 microseconds. Anytime I got a number between 0 and 1 microsecond, I'll put it in this bucket. Anytime I get one between 1 and 2, I'll put it in this bucket. And so I'll end up with some sort of a histogram right here. So I end up with some sort of a histogram right here. So it's just going to keep going like this. Now, if you were to plot out this curve right here, these points right there, these points would follow an exponential decrease right here. It would actually, and so you've probably done that in math, where this would follow as some e to the minus lambda t, where the half-life is the natural log of 2 all over that lambda when you fit it. Or you could just say, well, how far out do I have to go before this cuts in half? And then I go out that distance again, it cuts in half, and I go out that, it keeps cutting in half. So we could get, this experiment would take a couple of weeks to do, but you could do it right here, and you get the half-life of the muon. Remember, it had to stop right here, so we're in the proper frame. So the half-life of the muon is 2.2 microseconds, 2.2 millionths of a second. That's the half-life. So now that we know what the half-life is, maybe we can test some relativity. Suppose we take these two objects, just grab two of these, and go up to the mountains. Say you go up to the high Sierras. You can drive up to, say, 10,000 feet, go up to Mammoth, and here's your one detector. And now I'm going to separate them a little ways. I'm going to separate them by, say, 1 meter. I could separate them further, but 1 meter is good. And again, I'm going to go through my PMTs, photomultiplier tube, go through my discriminator, PMT, to turn it into a digital signal. So here's my discriminator, and then I get a digital signal, and then down here, digital discriminator, and I get a digital signal. Okay, now you can see that this one, since the muons are going down like this one's going to hit first, this one's going to hit a little bit later, because it's not going, it takes a little bit of time to go down there. Now, and the quicker this moves, the faster they're going right here. Well, let's say I only want the fast ones. Let's say I only want ones that are going greater than 90% the speed of light. Right here. Well, how long does it take, since we know what the velocity is and we know what the distance is, we know how much time that takes to move from there to there. The time then, between here and here, the time has got to be less than about 4 nanoseconds. 4 nanoseconds. If you're more than 4 nanoseconds, then you're going slower right here. So what I'll do is, I'll make this one, let's say 4 nanoseconds wide, 4 nanoseconds. And this one I'll make really short. And now I'm just going to AND these two together. I'll just AND them, put them in logic and AND them through. Well, as long as this one comes between here and here, I'll get a pulse out. So this will only count how many muons were going faster than 90% the speed of light. So all I have to do is count these. Say, let's just say I count them and I get 100 per second. I don't know what it is, but it depends on the area and all that. But let's just say you get 100 counts per second. Okay. So now what we should say is, since they only have a half-life of 2 microseconds, how far will they travel before they decay? Right here. Well, we know the distance is equal to the velocity times, and for the half-life, we know what that is. That's 2.2 microseconds, and we know the speed. We know it's at least 90% the speed of light. So if we plug in 90% the speed of light, so it's 0.9, and then the speed of light is 3 times 10 to the 8th meters per second. And then we plug in the half-life, which is 2.2 times 10 to the minus 6 seconds. This will tell me about how far they'll go before they decay. Well, and this gives you about, this is about 600 meters. Well, which is like 2,000 feet, which is around 2,000 feet. So let's say when I did this experiment, I was up at Mammoth, which is, let's say, 9,000 feet in elevation. So you did this up at 9,000 feet in the mountains. So now let's drive down 2,000 feet. We'll drive down to 7,000 feet. So now you come down to 7,000 feet and you do the experiment again. Well, if you've gone down a whole half-life, you would expect the count rate to get cut in half because we've gone through one half-life. You'd expect it to be 50 counts per second. And then if we go down to 5,000 feet, another 2,000 feet right here, we should be a quarter, another half-life. Instead of 50, it should be 25, and then keep going down. It should be keep cutting in half every 2,000 feet. So this would give me, say, 50, and then at 5,000 feet, I should get 25, and at 2,500 feet, I should get half of that, and so on. But you don't get that. You get a lot more. Why is that? Well, it's because the muon right here, his half-life is only 2.2 microseconds when he's at rest. He's not at rest. He's going 90% the speed of light. So his clock is running much slower. How much slower? Well, if you plug in the gamma for that, gamma, remember that gamma 1 over the square root of 1 minus v squared over c squared, is almost 3. It's almost 3, which means that they're going to live 3 times longer than you would think they'd live. So instead of getting cut in half every 2,000 feet, they're gonna live 3 times longer, so they're not gonna get cut in half until every 6,000 feet. So you're gonna have to go all the way down to 3,000 feet before they get cut in half. And so they've measured this. They last a lot longer the faster they're moving. You could have just looked at the slow ones, or the faster. You could change the time right here. And the faster they're moving, the further they'll penetrate right here, more than they would classically. Now, if you're sitting on the neutron, on the muon, if you're sitting on the muon, how do you interpret making it to the Earth? Because if you're on the muon, you say, I'm going to die in 2.2 microseconds. So how do you explain it from the muon's point of view? Well, from the muon's point of view, he says, yeah, okay, I might die in 2.2 microseconds, but this length between the 9,000 feet and sea level does not look 9,000 feet to me. It appears shrunk. By how much? By a factor of 3. Remember, we know length is going to be decreased. And so he'll say, hey, you're only 3,000 feet. And so I can make it to the ground right here. So in both ways it happens, but they explain it different ways. From our point of view, we say, no, you live longer. From the muon's point of view, say, no, I don't live longer. The distance shrinks. So this is one way you can just show that relativity works right here. And it's been done many times right here. Okay.